Let's start with what SARSA actually means. The name comes from the sequence of steps it uses while learning. That's state, action, reward, then the next state, and the next action. That's why it's called SARSA, and it literally follows that chain S, A, R, S prime, and A prime. And okay, now what is the point of all this? SARSA is a reinforcement learning algorithm and it is similar to Q-learning, but there is a key difference. SARSA is what we call an on-policy method. That means it updates the value function using the action that was actually taken, not the best possible action. So it sticks with the policy it's following, even if that policy is still exploring. And because of that, SARSA tends to play it a bit safer. It's more cautious about risky actions compared to Q-learning. If your policy includes exploration, like taking a random move from time to time, SARSA takes that into account when updating its value estimates. Q-learning doesn't. It just assumes you are always going to take the best action next. Okay. And alright. Now let's walk through how the SARS algorithm flows step by step. We start in some state. We will call that S. From there we pick an action A that's based on our current policy, could be epsilon greedy or something else. After taking that action we receive a reward that's R. And then we land in the next state and it is S prime. In that new state we pick the next action A prime, again using the same policy. This full sequence from S to A to R to S prime to A prime is the core of SARSA. Now, how do we actually use this to update the Q values? That's what this equation shows here. Look at here. We take the old Q value for the current state and action, that's Q of SA, and we update it by adding a correction term. That correction is the learn rate, alpha times the difference between what we got, the immediate reward, plus the discounted Q value of the next state and next action, and what we expected, which is just the old Q value. And okay, so in equation form it looks like this. Q of S A gets updated to Q of S A plus alpha times the bracket term reward plus gamma times Q of S prime and A prime minus Q of S A. And gamma is discount factor. It tells us how much we care about future rewards. Alpha is learning rate, how fast we adapt to new information, and Q is our action value function. And the table or network that holds what we have learned so far. And okay, let's look at here first here. What's happening here? Now we will go to an actual Q value update step by step using the SARSA algorithm. Okay, and we start off with our initial Q value for a given state action pair, and let's say Q of SA, and in this example it's sitting at 0.5. Okay, that's our starting estimate for how good that action is in that state. Then we take the action and observe what happens, and we get a reward, and in this case the reward is 1.0. So we did something that turned out to be pretty good, at least immediately. But hold on. Next. SARSA doesn't just look at the immediate reward. It also considers what we expect to get in the future based on the next state and action we take there. So now check the Q value for that next step, and that's Q of S prime A prime. Let's say that value is 0.7. This is basically our estimate of the value of continuing with the policy from that point on. And okay, temporal difference here. And what's happening here? We need to compute what's called the temporal difference, the TD here. This measures how far off our original guess was. So here's how we calculate it. It's the reward plus the discounted estimate of future return, that's gamma times q of s prime a prime minus our current q of s a. Okay, so let's actually plug in some numbers. We have got r is 1, q of s prime a prime is 0.7, gamma, let's say it's 1 just to keep things simple, and q of s a is still 0.5. And here we can see, and that's okay. And here update q value. We take that TD error and scale it by alpha, which is our learning rate, and here alpha is 0.1 again, and that's okay. So the update becomes q of sa gets updated as 0.5 plus 0.1 times 0.13, that's 0.5 plus 0.13, which gives us the new q value, and it is 0.6 what is the 61. Okay, and I hope that's okay. And let's look at this here, what's happening, and here's the epsilon part. This one uses what's called epsilon greedy strategy, and the idea is pretty simple. Most of the time agent chooses what it thinks is the best action, but every once in a while with probability epsilon it just picks something random to explore a bit. And let's see how it works as we adjust epsilon. So here let me switch. Okay, when epsilon is 0.5, the agent is most exploiting about here 100. Okay, and here let's make it 0.2, run again, and here you can see, and let's make it 0.3, and here exploration, and again 0.4. So here we can see epsilon, and look at our exploration and exploration rates, and again you can see 0.8, and exploitation is less, and let's 0. Okay, and finally here all of them is orange. Okay, and let me next part. Okay, here's the our comparison table for SARSA and Q-learning, and that's okay. And first policy type, what's happening here? SARSA is what's called an on policy method. That means it updates based on the actual it takes, and including any exploratory moves. In contrast, Q-learning is off policy. It always updates using the best possible action in the next state, no matter what action was actually taken. So it's assuming a sort of perfect behavior down the line. Update the formula here. SARSO uses the Q value of the next state and the actual action taken, that's Q S prime A prime, while Q learning uses the maximum possible Q value in that next state. So maximum possible Q value, and again more optimistic. And because of that, their behavior differs. SARSA is a bit more conservative, since its own policy, it accounts for the fact that we might take a risky move due to exploration. Q-learning, on the other hand, is more optimistic. It assumes we are always gonna follow the best possible path, which sometimes lead to risky decisions near edges or penalties. And lastly, in terms of convergence, SARSA converges to whatever policy it's actually following, even if that includes some randomness. Q-learning aims to converge to the optimal policy overall, regardless of what path it took during training. Now, if you look at the cliff walking example just below, the difference becomes more intuitive. Here, the blue dashed line is SARSA. It avoids cliff by taking a longer route around it. That's because it knows that exploration might cause it to fall off. It's playing it safe. Meanwhile, the here green solid line is Q learning. It hooks the edge of the cliff. That path is shorter and under the assumption that we act optimally every time. It's better, but it's also riskier. If we ever make a random move, we could fall into the cliff and get a big penalty. And that's all for this lesson. And thank you for listening. See you in the next class.